Welcome to the Explainer. Today, we're putting on our hard hats and tackling a classic engineering challenge, the graph deep copy coding problem. Think of it like constructing a brand new building from a master blueprint. We're not just moving into an existing house here, we've got to build an exact replica from the ground up, ensuring it stands entirely on its own. All right, let's dive into this.
So before we pour the foundation, we really need to understand the golden rule of a deep copy. It basically means creating a completely independent clone of a graph by making brand new nodes, rather than reusing any nodes from the original graph. We literally cannot just point to the old graph's addresses in memory. We're building an entirely independent structure, node by node, wire by wire.
And this means total independence. I'm talking absolutely zero references back to the original graph. If the original graph completely vanishes tomorrow, our clone graph shouldn't even blink. That's the level of separation we need. Okay, here's our blueprint for today. We'll start with the deep copy challenge, then look at graph traversal with DFS, and connecting the neighbors. After that, we'll tackle avoiding infinite loops, bring in the HashMap solution, and finish up with measuring algorithm complexity. Let's get right into it. All right, part one, the deep copy challenge and understanding our constraints. Moving right along to part two, graph traversal with DFS. This is really our primary building tool. So before we actually start building, let's lay out the constraints. We're starting with a reference to a single node within an undirected graph. Every node has a unique value and, luckily, is completely reachable. Our strategy here is to traverse the original graph and clone each node as we go, using depth-first search, or DFS. When we call DFS on our input node, it does this highly predictable three-step rhythm. Step 1, clone the current node. Step 2, DFS through its neighbors. And step 3, connect the cloned neighbors. It's just a clean, logical loop. Isolating that very first step, we start with our input node, node 0. The absolute first thing our DFS function does is create a standalone copy of that node. Boom. We've got a cloned node 0. But, well, right now, it's just kind of floating there in space, totally disconnected from the rest of the world. Which brings us to part 3. Connecting the neighbors and wiring up the network. Because, let's be real, a standalone node isn't a functional graph. To get this wired up, we execute step 2. From our freshly cloned node 0, we send out recursive DFS calls to its original neighbors, node 1 and node 2. Each of these new DFS instances will do exactly what we just did, create a clone of their respective input node, and then check for their own neighbors. And here is where it all snaps together. Step 3, returning the cloned nodes and connecting them. Once those recursive DFS calls finish building node 1 and node 2, they send those cloned nodes right back to our original call at node 0. Our cloned node 0 then adds them to its neighbor list, securing those connections. Our new network is officially coming alive. But as with any complex construction project, we're about to hit a massive structural hazard. Moving to part 4, avoiding infinite loops and the dreaded cycle problem. You see, graphs are tricky because they loop back on themselves, forming cycles. And in recursion, a cycle is incredibly dangerous. So let me ask you, what happens if a node has already been cloned? Seriously, think about the implications here. If node 0 calls DFS on node 1, and node 1 loops back and calls DFS on node 0, and we just blindly keep creating new clones every single time we see a neighbor, we're going to get trapped in an infinite loop of creation. Our program will just crash. We desperately need a way to track what we've already built to prevent all this redundant work. Enter part 5, the HashMap solution. This is going to be our node registry. This is the absolute hero tool of our explainer, a total eureka moment. We can manage this whole cycle problem beautifully by just using a simple HashMap. We use the original node as the key and the newly cloned node as the corresponding value. It acts as an official, centralized registry of every single piece we've constructed so far. Let's visualize why this registry is such a game changer. Consider node 2 at the bottom. Its neighbors in the original graph are nodes 0, 1, and 3. Let's say that during our traversal, nodes 0 and 1 have already been successfully cloned, but node 3 hasn't been cloned yet. So, to link our cloned node 2 to its proper neighbors, our algorithm fatefully fires off a DFS call to all 3 of them, node 0, node 1, and node 3. We are literally right on the brink of doing redundant work here, or worse, triggering that massive infinite loop by trying to rebuild nodes 0 and 1 entirely from scratch. But here is where the HashMap works its absolute magic. Whenever we perform a DFS call on a node, we first check our HashMap registry. Does it already have a clone?
For nodes 0 and 1, the answer is yes. So the hash map simply hands back those previously created nodes. No new cloning, no infinite loops, problem solved. For node 3, the hash map says, nope, haven't seen it, so we create a brand new node, add it to the hash map, and wire it up. It's just a brilliant way to balance building new structures while safely reusing references from our cloned registry.
All right, part 6, measuring algorithm complexity. Time for the final inspection. Now that our structure is fully constructed, you know how it is. As engineers, it's never enough that the code just works. We've got to evaluate how efficient our HashMap and DFS strategy actually is in practice. First up, time complexity. This measures out to big O of n plus e. Why? Well, because during our visual journey, we traverse through and create a clone of all n nodes of the original graph, and we traverse across e edges during those DFS calls. It perfectly matches the number of elements in our blueprint. Next is space complexity, which is big O of n. We have two factors here: the space taken up by the recursive cost stack, which can grow as large as n, and our hero tool, the HashMap, which stores exactly one key value pair for each of the n nodes. It is highly optimized, mathematically sound, and honestly pretty elegant. So we've successfully deep cloned our undirected graph using DFS and a really smart HashMap registry. But I want to leave you with a final, provocative thought to test the mental model you've just built. How would this HashMap strategy adapt if our graph was directed? Think about it. If the paths only pointed in one direction, would our cycle detection and cloning logic still hold up exactly as is? Or would our master blueprint require an update? Keep thinking about how these rules apply as you tackle broader, more complex applications. Thanks for joining me on this explainer, and keep building.